60 years ago today, humanity came of age. On April 12, 1961, Yuri Gagarin strapped into a metal ball less than 8 feet wide and became the first human to leave planet Earth and step out into the universe. Exactly 20 years later, the space shuttle launched, bringing science and exploration into orbit. In the years since Gagarin's flight, we have walked on the moon, sent probes across the solar system, and even beyond it. Today, we're entering a new era of exploration. So happy 60th birthday to our spacefaring civilization.
Welcome everybody to the Breakthrough Discuss Yuri's night celebration. Most years we would have done some celebrating with beverages, including adult beverages. Unfortunately, this year we're here virtually with each other. But very exciting things have happened, and as we heard about today, the Alpha Centauri system beckons and is very exciting. But this evening, we're going to focus back on our own solar system. And in the last few years, we've learned a lot of possibilities in our solar system for where there's life. You can see pictures behind me of 5 of the objects that had a lot of discussion. In the last year, though, of course, the planet Venus had particular focus. So we're going to focus our discussion tonight on Venus and beyond. Without further ado, I'd like to introduce Professor Sarah Seeger from MIT, who is been a principal in a lot of the research on Venus and on exoplanets, and a co-author of the key paper. And she's also doing a study for the breakthrough initiatives on potential missions. Over to you, Sarah.
Thank you. Good afternoon, good evening, everyone. We're here to celebrate Yuri's night and to tie together astronauts and Alpha Centauri system and Venus. So we're going to get started right away. And our first speaker tonight is John Grunsfeld. And while we're waiting for John to come on and me to share my screen, we have our panelists who all speak for a few minutes each. Then we will do a poll, and then we'll have time for some Q&A, both among the panelists and taking questions from our Q&A for our attendees. So John needs no introduction. We heard him before from the keynote earlier today. So welcome, John.
Thank you very much, Sarah. Sarah and I have worked together for many years, and I think it's a good, and many of the other folks, Pete Warden, perhaps for even longer, and it's a good introduction really to tonight's Happy Yuri Night celebration, because on April 12th, 1961, Pete was a little older than I was. I was 3 years old. So I don't remember this, but it's the launch of Yuri Gagarin departing the Earth as the first human being to orbit the Earth is a metaphor for so many things. The start of the space age. One might say that Sputnik was the start of the space age, and indeed, it was the first man-made object to be sent to orbit the Earth. But after all of exploration is human exploration. Even when we send robots to Mars, the Curiosity robot, now the Perseverance robot, they don't discover anything. It's scientists here on Earth, people like Sarah Seeger and others who discover things using those tools. But in the case of Yuri Gagarin, he was the first to go. He was the daring individual who not only launched on that Vostok 1 rocket, but who had to enter the Earth's atmosphere as a fireball, and then at a little under 10,000 meters, had to jump out of the Vostok capsule and parachute down to Earth, where he encountered a woman and her daughter, a farmer's field, where they were planting potatoes, and they had no idea whether Yuri in a spacesuit was an alien or a fellow Soviet citizen, which he established rather quickly. But really an incredible flight. But as I said, it was a metaphor for, human exploration. I think as long as humans have had cognition, we've looked up at the stars and wondered, what are those bright lights? Are they, other worlds? Are we alone in the universe? And so Yuri Gagarin and the space program of the time inspired so many people. It inspired me as a young boy to look up at the stars and wonder, are there, other civilizations out there? Because as I grew up, we had the Mercury flights, we had the Gemini flights, we had Apollo. And so for me, I grew up thinking that space flight, although still in its nascent form, was the norm. And I think that's really what changed the world, that has helped us inspire, subsequent generations to want to go to space. And of course, many hundreds of people now have gone to space. And I think what we'll find in the next generation is that it will be thousands of people and then tens of thousands. And the question is, where will we go? Next slide, Sarah.
Got it.
Thank you. The next slide, well, we're going to go out into our solar system. And I haven't included Earth's moon in here because there's another theme for this slide, the search for life. But right now, life is an N of 1. And many of us on this call and many of you listening would like to increase that number because we're all curious about, whether there's life out there. And as a physicist and just as, physicist who looks at the numbers, the statistics, that there's hundreds of billions of stars in our galaxy, that there's a high proportion, perhaps nearly every star that has a solar system around it, that, whatever the exact number you want to choose, that there's probably 20% that have a rocky planet about the size of Earth and some fraction of those in a habitable zone. You end up with, 40 million candidates for planets like Earth. And that doesn't include moons. And so it's just incredibly exciting that there's almost got to be life out there. And for the first time in human history, we have not only people leaving the planet to go to space, people living in space on the International Space Station, but we have the technological means to go to worlds in our solar system, to interrogate worlds outside our solar system, and to find out the answer to the question of, is there life out there? And in our solar system, we have incredible diversity. And while Mars may be the only planet in our solar system that would really be a nice place to live, if you call it a nice place to live, I would want to live there. But we have, the potential for life on Venus that we'll discuss tonight. We have ocean worlds like Europa and Enceladus that are probably teeming with organics, if not life. And we have Titan, which is a prebiotic world that also has a subsurface ocean that we're going to interrogate Titan with a drone called Dragonfly. So I'm really excited with this panel, and I'll hand it over to the next speaker. Thank you.
Thank you, John. While we're waiting for David to come up, I'll give him a brief introduction, although David Grinspoon needs no introduction to the Venus community. David is an outstanding Venus scientist. He's an award-winning author. He works on a lot of different planetary missions, and we're lucky to have him here tonight. Welcome, David.
Thanks a lot, Sarah, and welcome to Yuri's Night, everyone. One area where the Soviet space program was incredibly successful was the exploration of Venus. Although the first spacecraft to successfully encounter another planet was Mariner 2, which launched on an Atlas Agena rocket, seen here, on August 27th, 1962, and flew past Venus on December 14th, 1962, which incidentally was exactly 1 week before my 3rd birthday. Mariner 2 carried with it a microwave radiometer, which was the first scientific instrument successfully sent to another planet. And in my view, it's still the best example of hypothesis testing in the entire history of planetary exploration. At that time, there were 2 competing ideas for the anomalous microwave radiation seen coming from Venus. Either Venus was really hot on the surface, likely due to a very strong greenhouse, atmospheric greenhouse, or else there was some kind of upper atmosphere phenomenon causing that radiation. If it's coming from the surface, it should be limb darkened as seen in this bottom image, because the radiation has to travel through more attenuating atmosphere at the edges than in the center. This would mean Venus is too hot to be at all like Earth. If it's coming from the upper atmosphere, you'd see limb brightening, as in this top image. The flyby worked, and the scans revealed an unambiguous signal of limb darkening. That showed that Venus is hot and not at all Earth-like. But how hot? And how high was the surface pressure? The first spacecraft to enter the atmosphere of Venus or any other planet was Venera 4 in 1967, an incredible accomplishment. Venera 4 measured conditions in and below the clouds and descended until it stopped operating at 18 atmospheres pressure and 500 degrees Fahrenheit. At first, they thought it had reached the surface. The very next day, Mariner 5 flew past Venus. The results combined with the Venera 4 results helped put together the first decent models of the atmosphere. So even while the Cold War raged, there was significant cooperation between the planetary scientists on both sides. And it turned out that Venera 4 had not reached the surface, but it had been crushed at an altitude of more than 16 miles. So spacecraft would have to be built more robustly and endure higher temperatures and pressure. Finally, in 1970, Venera 7 was the first to reach the surface while still functioning. Unfortunately, it fell over on reaching the surface and thereby lost contact with Earth. But Venera 8 in 1972 landed and functioned for almost an hour on the surface of Venus. Among other things, it measured light levels and found that 2 to 3% of the sunlight reached the surface, equivalent to a deeply overcast day on Earth, meaning there's plenty of light to see by, meaning that future spacecraft should have cameras. Next slide, please. Emboldened by the success of Venera 8, the Soviets built a new generation of Venus craft, each with an orbiter and a lander. And the landers all looked like this image here in the middle. They had a story using very Russian humor about this event. He said, during the landing of Venera 11, the science team was gathered for the return of the first photos, with some of the military brass there observing. The first image came back all blurry and murky, and the camera designer said, "We seem to have landed in a dark, viscous liquid." To which another team member responded, "Yes, we are in deep shit." Anyways, they continued onward, making incremental improvements every 19-month launch window. And in 1982, Venera 13 and 14 successfully did return the first color panoramas. And you can see on the bottom here, one of those Venera 14 color panoramas. There was another weird mishap with the lens cap on Venera 14. You see that little arm thing that had a penetrometer that was supposed to spring down and penetrate the surface, thereby measuring the properties of the rock, the hardness and so forth. However, you can see that penetrometer never reached the surface. Instead, it encountered an artifact of a technological civilization, the lens cap. And they later calculated there was a 1 in 1,000 chance of that problem, but the lens cap popped off and the darn penetrometer hit the lens cap instead of the rocks. Oh, well, other than that, a very successful mission. Anyways, all of that preliminary exploration by Americans and Russians set the stage for Magellan, which then mapped most of the surface between 1990 and 1994 with radar, showing Venus to have a diverse and complex surface, geologically young compared to most of the solar system, with a long history of tectonic and volcanic activity. And this really leads to our modern view of Venus. And the cartoon in the upper left is my attempt to capture that. And I want to leave with one last point, that those of us who suspect the clouds could be habitable, that's not just because the conditions there are relatively benign, which they are, but also because of these geochemical cycles fueled by both surface activity and the energy of sunlight, which create a chemically fertile environment that we just need to go and explore further. So we have continued to explore with 2 small orbiters, Venus Express and Akatsuki, and these have confirmed complex dynamical and chemical cycles in the atmosphere and added more evidence for surface volcanism. These are great missions, but there's only so much you can do with small orbiters. It's time to take the plunge back into Venus with new missions, and we'll be hearing more about that with the other panelists.
Thank you so much, David. Fascinating. We're now ready for our next speaker, Bethany Ellman, Professor of Planetary Science at Caltech. And Bethany is also the PI of the Lunar Trailblazer mission to map water on the surface of the moon. Welcome, Bethany.
Thanks, Sarah, and thanks to everyone for joining. Happy Yuri's Night, everyone. I'm excited to be with you on this evening where we just get to celebrate our accomplishments as of a species as we head out into space. I have to tell you, so I'm a geologist by training, and photos like the one that you're looking at here of the Curiosity rover at a cliff named Mont Mercure are just, you know, the thing that I most want to explore as I go out, whether it's boots on the ground or robots on the surface. What I'm most interested in is understanding deep time, understanding the evolution of the worlds that we live on. We know that the Earth that we're on today was once not the same as the teeming abode of life that we have it now. It evolved into that. It grew into what it is over time. You know, as we push outward with the Breakthrough Foundation, Breakthrough Initiatives, and consider missions beyond to exoplanets like in the Alpha Centauri system, one of the things we're really fortunate to have is to guide the questions we ask and how we explore are these 3 terrestrial planets in our solar system. For 100 years, we've been probing Earth's record in detail, able to crawl over all aspects of the surface. In terms of Mars, it's been really a renaissance since the 1997 Pathfinder rover. I have been really fortunate to be a part of 4 rover missions now, counting Perseverance, where we are really trying to understand why Mars is the way it is today. Why is it cold, dry, hovering at the edge of habitability? There's ice underground, maybe liquid water, maybe even life. But if we were to transport ourselves 3.5 billion years ago to rocks like those that you're seeing on the screen right now, those layers, those thin laminae, you would see that those were deposited in a salty body of water filling the bottom of Gale Crater. So why was Mars that way? You know, further away from the sun than Earth, cold, but yet it had standing bodies of water. Why was it that way? Did it develop life in these environments, these lakes, these rivers, these hydrothermal systems that our program of exploration has seen and developed? Well, we're not done asking those questions of why, of how, of is Mars inhabited yet, but we're on the way. And so if we go to the next slide, the planet in our solar system, the terrestrial planet that needs some attention for asking these big questions of, you know, how do habitable planets evolve? How or why are they sustained through time? Or why are potential habitats for life lost? Well, the linchpins in the solar system are Earth, Mars, and Venus. And this picture of the surface of Venus from Venera 13 and 14 both landed within months of each other, and they both landed before I was born. And so it's been that long that we've left this other sister planet that has some of the clues to these big questions about how planets work unexplored. So I'm so excited by the excitement that you heard David talk about with regard to Venus. I'm excited by the fact that there are 2 Discovery missions in competition in the NASA competition right now that target Venus. The Japanese Space Agency has an orbiter studying the atmosphere, and I'm really excited by the Breakthrough's study of also the potential for investigation of the Venus upper middle atmosphere as a potential habitable zone in this solar system. You know, we only get so many shots, so many places to look for life nearby. So let's take them all, right? Let's figure out how rare or how common is life in the universe. So I hope we get down to the surface of Venus, to those rocks, to explore the history. When did Venus last have an ocean? When was it last habitable? But I hope we also target that upper atmosphere as we, you know, continue to explore our solar system, and then also to worlds beyond. So with that, I'll turn it over to the next panelist.
Thanks, Bethany. Wonderful. Let's do it. So our next speaker is Dr. Yanish Petkowski, who is a research scientist at MIT. Yanish is a biochemist, and he also plays a leading role on the Breakthrough Initiative sponsored study for mission or missions to go to Venus and search for signs of life, or maybe even life itself. Welcome, Yanish.
Thank you, Sarah, for a very kind introduction, and welcome everybody, and thank you for the invitation. I really look forward to our discussions this evening. And what I'm going to talk about over this couple of minutes is I'm going to try to make a case for an astrobiological study of Venus. We have heard from David and Bethany quite a bit of information about Venus already. I'm going to focus on the clouds and the fact that they are really a very mysterious place, and at the first glance they might not actually seem to be habitable, as they are made from little droplets of concentrated sulfuric acid, a substance that is nothing but habitable for life as we know it, at least. But it might very well be that it was not always like that, because Venus actually had most likely a very tumultuous history. Could we go to the next slide, please? If some climate modeling is actually correct, then Venus likely had a very clement past with surface water oceans, rivers, and seas that lasted on the surface of the planet for as long as a couple of billions of years, maybe even until as recently as 700 million years ago. So we can actually speculate potentially that what if life actually originated on Venus and then thrived on the surface of the planet for billions of years and eventually adapted to the environment as the environment deteriorated into this hellish state that we know today. Maybe life actually adapted to it and escaped, so to speak, into the only place that actually was habitable for it from the point of view of temperatures to the clouds. Of course, we do not know if this indeed happened like that, but we can actually put forward such a hypothesis, especially that there are chemical mysteries in the clouds of Venus that are actually quite spectacular. Can we go to the next slide? And one of the most profound chemical mysteries in the clouds of Venus is the so-called mysterious UV absorber. So it's a chemical or chemicals that absorb approximately 50% of all the UV light that fall onto the planet. And over the decades of studies, people do not really understand what it really is, what is responsible for that. And especially that this phenomenon, this mysterious UV absorber, is actually very dynamic in space and time. And it actually also follows a quasi-seasonal changes. So, but people claim that it might actually be some complicated sulfur chemistry, but nothing really seems to fit. Apart from that, we have other multitude of various chemical mysteries in the clouds of Venus that go beyond that. Can we go to the next slide? Over the couple of years and over the various measurements that people were doing regarding the composition of the clouds, people were able to actually identify or tentatively identify a couple of various gases in the atmosphere of Venus that do not really belong there. And the newest such mysterious discovery is tentative discovery of phosphine gas in the clouds of Venus. All of those chemical mysteries are actually, if indeed confirmed, are essentially produced by some sort of chemical processes that are unknown and maybe even life. So can we go to the next slide, please? So we are very fortunate because Breakthrough Initiatives is now sponsoring an MIT-led study of a mission to Venus to search for life itself or signs of life. So this is a series of studies that actually have the astrobiology as its core, and we have three different missions or concept studies that we actually explore. There is the so-called small mission that we hope to partner with Rocket Lab in development of. That is actually a very focused mission to detect various signs of life in the clouds of Venus, including specific gases, and even measuring the properties of the aerosols. We also have the medium mission that actually is inspired by the Russian Vega balloons. It is much more sophisticated and much more complex in terms of the instrumentation on board, and it not only searches for signs of life in the clouds of Venus, but also for the life itself. We hope to actually capture the aerosols, for example, and have an imaging system that allows us to maybe even visualize whatever those aerosols are actually made of. And apart from that, we also hope to look for various complex organics if they are there. And finally, we also have the large mission, the so-called large mission, which we hope to be atmospheric sample return mission. So we know that the clouds of Venus, in terms of the temperature, are the place on the planet that is potentially habitable. So we would love to actually scoop and collect some of the aerosols in the atmosphere and actually bring it back to Earth to study in detail in our own laboratories. So this is, thank you very much. So this is essentially, I look forward to our discussion and any questions that people have.
Thank you, Yanish. And certainly we can welcome more questions about the plans for the wrapping up the mission concept study. All right, well, I have a few remarks before we move to our Q&A. And I just want to say I love how John Grunsfeld started us off by saying, space is the norm. And indeed, anyone born after the dawn of the space age, until he said that, for me, yes, it's the norm. And today, it's amazing that exoplanets are the norm. And sometimes I look at my undergraduate students or graduate students, and for them, exoplanets have always been around. As soon as they came of age to understand the world around them, exoplanets were always there. And now we're in a phase where we're trying to move the field so that habitable planets are the norm. And we're so fixated on Earth as an exoplanet and trying to find the other Earth, but sometimes we wonder, what if everything turns out to be like Venus? In fact, what's really interesting is to any of our current planet finding techniques, Earth and Venus would basically look the same. They're about the same size, about the same mass. And although there are different distances from our sun, if we were to find the Venus-Earth pair, we wouldn't necessarily be sure which one, if either, is habitable. But we know, of course, that Earth is a nice habitable world, and Venus, at least at its surface, is far too hot for any kind of life as we know it. We heard already from others in this panel that Venus is a dynamic, compelling planet with volcanic and other geologic activity. It's got these crazy winds that go around the planet in 4 days. And there's a lot to learn there. It turns out that in terms of exoplanets, Venus is actually easier to find than another Earth. To transits, the most popular planet finding technique today, planets that are closer to the star are easier to find. They're more likely to transit, and we can bin the data more. That's not strictly true for sun-like stars, for which a Venus or Earth transit would be rare, but it holds for M-dwarf stars. Even for high contrast space-based direct imaging, where we'll block out the star to see the planet directly, Venus is closer to the star, but it's harder to block out the starlight. However, Venus is brighter than Earth because it's brighter than Earth in reflected light, much, much brighter, and therefore it is in some ways easier to see. So I want to give a shout out to Stephen Kane for calling Venus our planet next door, and for encouraging our community to take like a good look at Venus, better look, to revisit Venus with models and missions, because we really want to try to understand exactly how Venus ended up where it is. We think that Venus started with water oceans, and I want you to imagine for a moment that life originated on Venus long ago, early in its history, and that life continued to thrive in the Venus water oceans until we think Venus underwent a runaway, when the oceans evaporated and went away, at which time perhaps any life could have migrated to the atmosphere, to the clouds, and adapted to live in the very, very harshly acidic environment. And we do like to imagine, starting with Carl Sagan 50 years ago, and worked on and off by David Grinspoon and others all those years, about a biosphere, an aerial biosphere in the Venus clouds. And that's what I've been thinking about for a while. I'm not going to go into detail here. You can read this paper if you want, but we came up with a way to, quantitative way to think about life particles, small bacteria-like type particles inside cloud droplets, how they could stay aloft indefinitely. And so we like to think there's a revival of interest in Venus today. And that's partly why we're here tonight, celebrating Yuri's night, and what we hope is a bright future for Venus. So before we get to our Q&A, we are going to launch a poll to get your opinion on a couple of questions. So to the IT folks in charge, here's our poll. Do you think Venus was habitable early on through most of its history today? And my guess is you can only choose one. Do you think that Proxima Centauri b is more like Venus, Earth, or neither? And then 3, will a snapshot of the Alpha Centauri system yield multiple habitable worlds, one habitable world, or possibly no habitable worlds? And where should we prioritize the search for life? Wow, that's a tough one. Mars, Europa, Venus, Enceladus, or Titan. So if you can all fill this out, we will be able to come back to this a bit later. Okay, great. I think we're ready for our panel to all come back online. And we're going to first, I'd like to open it up to the panel ourselves to ask each other a couple of questions.
Well, I have an opening question, which is referring to something Bethany mentioned, which is we have 2 really interesting Venus missions in competition for the Discovery program, which is NASA's, it's a relatively large cost mission, but it's sort of its mid-sized planetary missions. Would, maybe for David, because I know you follow these things most closely, would either of those missions give us much leverage on this question, at least of atmospheric composition, if not the search for life?
Absolutely, yes. And full disclosure, I'm on one of those missions. So I have a dog in this fight, but the next thing I'll say is I would be absolutely thrilled if either of them gets selected. And I'm pretty hopeful that at least one of them will be. And my fantasy is that it's not impossible that both of them would get selected, because they're saying they may select 2 Discovery missions, and they're very complementary missions. And so it's not completely out of the question that then we would suddenly have a Venus program. And yes, they're both very relevant to this question. The Da Vinci mission, which is an entry probe, which full disclosure is the one that I'm on, is directly meant to measure a lot of the unknown atmospheric properties in terms of composition, and also get at some of the questions about surface history by doing some surface imaging on the way down. So it's very relevant to questions of atmospheric origin, evolution. It's not as specifically relevant to life finding. It doesn't do as much in the clouds as some of these other things we've been talking about and Sarah mentioned and Yanish mentioned, but it's, it's an important sort of atmospheric survey mission. And remember, we've never sent 21st century instruments into Venus. The last American entry probe mission was done in 1979. So we've got a lot of catching up to do. And the other mission is more of an orbital survey of radar and infrared, with these windows where you can see the surface and search for active volcanism. And again, that really will tell us a lot about this history, potentially history of an ocean. And, so general questions of the habitability history of Venus would be addressed.
Okay, I have a question, but I want to wait and see if any others, I do have a question. I know we're going to get asked this, so I thought I would just address it up front. And I just was looking for a brief answer from Yanish, and then let's go to David. Someone's going to ask us about phosphine on Venus. What is the latest here? There's been an awful lot of controversy, and I think the audience will want to know what the latest is on that.
Yes, I mean, there is as any novel discovery, this is going to be controversial because the stakes here are actually quite huge if phosphine discovery is true. So So what there are essentially two questions. Is the signal that was detected by Professor Jane Greaves and her team real? Does it exist? Is it statistically significant? And the second question, if the signal is statistically significant and is really there, then is it actually phosphine, or is it actually some other component of the atmosphere of Venus, for example, sulfur dioxide? And currently there were a couple of papers published that questioned the statistical validity of the phosphine detection. So they questioned if the signal itself is actually there, both from ALMA and JCMT telescopes, which were actually used in the phosphine detection. And there were also papers that actually claimed that the signal from JCMT telescope could be actually explained by the sulfur dioxide. And current state of the discussion, of the debate, is that essentially Professor Jane Greaves also replied with her own papers and showed that by statistical analysis that the actual signal is likely there. And she also argues that the explanation of the signal by SO2 is insufficient. Yes, so that definitely it likely is also phosphine. Now there is also a question which is currently being sort of back and forth. The newest paper by Lincowski that actually suggests that the signal is not necessarily coming from the clouds themselves, but actually is from much higher up in the atmosphere of Venus. And this also, Professor Jane Greaves currently is working on the paper that actually is going to also address this problem. But we have to also point out one very important point, that one cannot not have signal. So the critics of the discovery cannot all be correct as well, because one cannot not have signal, essentially. There cannot be no signal, and that the same signal cannot be SO2. So there definitely is going to be a lot of back and forth, and we simply need more information and also more observations. There is also a very important additional discovery or rediscovery in the phosphine debate, which is the reanalysis of the Pioneer 13 data, or neutral gas mass spectrometer, that was done by Professor Rakesh Mokul. And that reanalysis of the 40-year-old legacy data led to the potential discovery of phosphine in the cloud decks of Venus at the height of approximately 51 kilometers. Apart from all the other various mysterious molecules, like tentative detection of, for example, ammonia or other nitrogen species that could, for example, form the nitrogen cycle. So this is definitely an ongoing development. And also one important point, which I actually wanted to ask the panelists as well, the importance of the legacy data and the possibility of actual in-depth reanalysis of the data that were collected by the legacy probes, because I think that this is actually quite important endeavor to be done. Rakesh Mogul was the first to do this, and I think that we can actually discover even more in this old data.
Okay, so David, did you want to comment on phosphine?
Very briefly, because I think Janusz really covered it well, but I'm glad you mentioned this other detection by Rakesh Mogul and his group, because it's just kind of strange that they seem to have found phosphine, if they're correct, from a completely different archival data set. So I'd say there's still a question mark about phosphine, but the one point I also wanted to make is that, at least on the level of journalism, there's been some abuse of this story, and that when some of these reports came out really questioning the phosphine, and to me the phosphine is very much an open question, and I'm looking forward to further observations, and maybe ultimately in situ will be the way to really answer this. But a lot of journalists made statements when the phosphine came into question, saying, Well, so there isn't life on Venus because there's no phosphine. But those of us who've been interested in the possible habitability of the clouds of Venus for a long time, phosphine was never part of it. And when I heard about the phosphine, I was excited because any new detection like that is exciting. But if the phosphine goes away, as well it might, to me, it doesn't really have a strong bearing on the motivation for investigating the possible habitability of the clouds of Venus, because it was never really a prediction that anyone was making. So, you know, to be continued with phosphine, but let's not confuse that with the case for possible habitability in the clouds.
All right, very well said. Here's a question. I'm going to direct this one to Bethany. It's actually a basic question about the atmosphere of Venus. Why is the atmosphere of Venus so much more massive than Earth's, given that the planets themselves are roughly the same size and mass?
So the geologist gets to answer the atmospheric science questions. Venus the geology is involved in the answer to this question. So unlike Mars, Venus hasn't lost large fractions of its atmosphere to space or had everything sucked down into the crust. Venus has active volcanoes that have continually been replenishing the Venusian atmosphere over these many billions of years, and so it creates the peculiar chemistry that we see here, dominated by the sulfur dioxide. It really has to do with the huge effect of geology in terms of perturbing this system. So I think that's important to keep in mind as we consider Venus's evolution, but also the search for life on Venus, on other planets. Venus, Earth, and Mars, none of them are at equilibrium. They're in this state of disequilibrium, right? When the volcano goes off, the atmosphere must react, and disequilibrium is actually quite good for life. Disequilibrium means energy sources, and so it all wraps back to the place that Venus is an active world and worthy of exploration.
It really is, and I think it's worth pointing out we don't know what sets the mass of a planet atmosphere. So when we think of Proxima Centauri b, perhaps it's a crazy planet with a very massive carbon dioxide atmosphere, even more than Venus is, making it so hot. And I did want to add that in Earth's ocean, we think Earth had a lot more carbon dioxide initially, but a lot of it dissolved in Earth's ocean, taking away a lot of our atmosphere mass. Well, there are a lot of questions about the Venus clouds, and that they're very acidic. And someone is giving David a bit of a hard time for having said that it's a nice habitable environment, but I think David probably meant the temperature is good. And the acidity is so bad, someone asks, could any type of extremophiles on Earth survive in the Venus clouds? And Yanish, I'll let you take that one briefly.
Yes, so definitely the environment of clouds of Venus is unlike any environment that we have here on Earth that is inhabited. So it's an environment that is unique. That we have to also realize that the acidity of if we really understand the clouds of Venus correctly, then they are made from concentrated sulfuric acid. This acidity is much higher, orders of magnitude. It's much more acidic than any other place inhabited on Earth, but even by the most hardy acidophilic bacteria or archaea. So there is no comparison there. So whenever we always talk about habitability of Venusian clouds, it is to a degree implied that this life has to, if it exists there, it has to be quite different than what we have here on Earth, at least in terms of adaptations to this very unique environment.
Right. We're going to switch topics slightly here because we have a question that has been upvoted, and this is, I'm going to have to put John on the spot here. It's a tricky one. What arguments would you give? Well, there's the question of what is your favorite astrobiology target? Let's start with that one because there's so many. You showed about 5 of them on your slide.
Well, my favorite current astrobiology target, of course, is Earth. We're still trying to understand, the dynamics of life on Earth and all the various environments. But, from a scientific perspective, I'm paying my attention to Europa. We have the Europa Clipper going there at the end of this decade, and it will arrive there at the end of this decade. But the intriguing plumes of water with organics at Enceladus has me paying my attention to Europa because it's a much larger ocean. It's almost certainly been a warm liquid ocean, salty ocean for 4 billion years with ocean rock interactions. There's probably a water cycle there. And it was probably formed with the same kind of organics that the rest of the solar system was formed with. And so you have a warm, salty ocean with organics and tidally driven rock ocean interactions. And so if you think of it like an old coffee pot percolating, it's had plenty of time to kick off life. There's some questions about maybe it's been too long and it's depleted all its nutrients. But it looks really intriguing. And because the surface is so young, less than a 50 million year old turnover time, we don't see a lot of craters. There has to be some process that's exchanging, the ocean water to the surface where it freezes. And that ocean is completely protected from the radiation environment around Jupiter. So it's an intriguing place. It's just hard to get to.
Very hard, yeah.
On the topic of Venus, though, switching topics a little bit, just to give something that I've said for years, people talk about terraforming Mars, and that's a really hard thing to do. It's very hard to create an atmosphere where there isn't enough. And I've said, if we wanted to terraform a planet, we might look to Venus, in that it has too much atmosphere. And if we could make it optically thin, we could perhaps make it habitable. Now, of course, in the long run, you don't really want to go racing towards the sun. You want to go away from the sun.
Well, there you go. And so this question was a little more specific. And what arguments would we give for prioritizing an astrobiology mission to Venus instead of Europa or Enceladus? We don't like to compete with each other, by the way, but this team here is really, really biased towards Venus.
Yeah, I mean, I'm going to punt a little bit, and then I'm going to kind of answer the question, which is to say, I'm incredibly excited to be living in the period of history that I'm living right now, because it's really the first time that we've been able to send missions out to the solar system to really ask questions about astrobiology and the search for life. We have reached that point where we have the instrumentation where we can go to these places, Enceladus, Europa, Mars, Venus, perhaps even other destinations, right? And really ask the life question. So in that sense, I think we should prioritize going to those destinations where we can ask and answer astrobiology questions. That said, I think we should step up our exploration of Venus. I think, right, Venus is in many ways the twin of Earth. We only have 3 planets that are rocky planets with atmospheres to train ourselves on, to learn how to interpret these exoplanets that we're discovering around other stars. And heck, Venus is close. It's accessible. You can get there. It doesn't take as long to get to Venus as it does to Enceladus. So let's send a bunch of missions. Let's not just do big. Let's send quick focused missions to specific questions like the search for life. And I think, what's really exciting is there are people on this call, right, who can help enable this future.
Okay, so one thing I always think about on exoplanets is we're very limited in our search for life, right? We're assuming that life uses chemistry like we do to extract and store energy, and that life metabolizes and gives off gases that will fill the atmosphere. So if there indeed is phosphine in the Venus atmosphere, like an exovenus, we'd never see that amount of phosphine. At parts per billion, it's just not accessible to us. Likewise, in exo-Europa, we couldn't, or at exo-Enceladus, it just would be off the table for us. So I like one of these really interesting question here. It is a breakthrough conference. We like to be provocative after all. This is a question from Lee Cronin, and he's kind of posing something parallel to what I just said. So I'll just read the question, and hopefully Yanish can take a stab, but it may be beyond what we can address in the short time we have here. And this is about, from an inorganic chemistry point of view, the prospect for really strange life on the surface, as well as in the atmosphere, is very compelling. Lee says, I don't think we should be bound by anything on Earth. So what does the panel think about inorganic in the search for life on Venus? So you can decouple surface from going inorganic.
I can briefly answer that. I thank you for that question, because it's actually a very interesting problem of alternative chemistries for life, or how really diverse life can be chemically. To be honest, my honest answer is I don't know. We could, in principle, envision some more complex inorganic chemistry, like, for example, boron nitrides or some other chemicals like that. Organic chemistry, as we do not expect to survive under the conditions of the surface of Venus, maybe beyond some rather boring Teflons. But yeah, definitely, I would never discourage anybody from exploring the possibility of very, very, let's call it alternative biochemistries that could in principle lead to life. Well, we should definitely do that.
Send that back to the audience if you want to reach out to us in the future. You hopefully picked up on what Yanish was saying before in his presentation, that we love this idea of sample return from Venus, capturing the atmosphere. And the part of that question is a lot more involved. What would we be looking for? What are we going to, how are we going to, preserve the sample on the way back? And even before we're even able to get a sample, what do we need to do to get ready for that? And so for you, it's, if you want to think about alternative life, try to wrap that into a question of what should we be looking for? So here's a really good question about Venus. Let me just get to it. This is a great one. This is a popular culture question. And I think it's directed to David. Have there been any movies or TV series significantly involving Venus since the old sci-fi of the 50s, 60s? And the thought is, raising the planet's profile might even encourage public support for sustained exploration.
Yeah, not enough. There's some good written fiction, some good novels. I guess that there is a Venus subplot in the Expanse. So I wouldn't say there hasn't been any, but I think the potential is great, because beyond our current phase of where we're talking about sending more robotic spacecraft to Venus, there are some very intriguing ideas about human-assisted exploration of Venus, which may sound crazy at first. You're not going to send people to the surface of Venus, at least very easily. But the idea of using humans in concert with machines on the surface to do the sort of things we do in the deep ocean of Earth, where you have vehicles which are teleoperated. You can't do that from Earth because of the time delay, but you could do it either from orbit or from stations in the clouds on Venus. So I see a time in the future where humans have a role in the scientific exploration of Venus. And then, of course, humans being humans, at some point, someone's going to decide they want to go and try to live in the clouds of Venus. So these are ideas that are out there, but not insane, and therefore I think they're good arenas for science fiction. And there are some books about it, but I think we do need more movies and TV shows about this. So anybody watching here who is a friend in Hollywood, please let them know.
There's at least one person here who has a friend in Hollywood. So, there actually was a response here mentioning The Expanse, and just remembered one of my undergraduate students from the fall told me to watch the Expanse, which has something on Venus on it.
So I have a question which I get quite often that I can't answer, and this is a good team to do it. But why is phosphine a biosignature gas, since we see it in Saturn and Jupiter's atmosphere and elsewhere?
Yeah, that is a good question. So Saturn and Jupiter have a lot of hydrogen. And beneath the atmosphere, the temperature is high and the pressures are high too. And so thermodynamically, phosphine wants to form. It's just a natural outcome of the basic equilibrium chemistry. On Venus, there's basically no hydrogen. And the temperatures and pressures, even though they seem high compared to Earth, they're nowhere near phosphine being thermodynamically favored in any way possible. So that's why Jupiter and Saturn have phosphine. And furthermore, on Jupiter and Saturn, we can have gases that get dredged up from below. There's a related question, though, and this one we definitely have had before, and I'll put this one to Yanish, is that can phosphine be created by volcanoes on Venus?
No, I mean, okay. It is always very important to put it in the context when we say no or yes when it comes to various chemical processes that produce molecules, because it all depends on the amounts that can be produced by a given process. And so the answer to that question is the short answer is that it is definitely not enough. If the detection of phosphine is correct, then we have a certain amount of parts per billion of phosphine in the atmosphere of Venus, and that requires a certain production, constant production of phosphine. And that production is insufficient if we actually invoked the volcanic or known geological processes of production of phosphine. So that's the short answer. If a viewer would like to have a very long answer, then we wrote a very long paper on the topics of what cannot make phosphine on Venus, and it's now a 127 page long paper that just got accepted in Astrobiology.
Yanish and I are on the Phosphine Venus team, and there has been a lot of publications about data, and some of these publications now actually contradict each other. Some find the signal, some don't. But there hasn't yet, to my knowledge, been a publication on a way to make phosphine on Venus. So no one in the community has yet, made a scientific paper that finds a viable way to make it that will come to the part per billion level. So let's stay tuned and see if any of that happens. So there have been a lot of questions here in the general topic of like panspermia or meteorites. So have we ever found a meteorite from Venus, either here on Earth or on the moon?
No, there are no meteorites identified from Venus. And it's an interesting question, why not, since we have a number of Mars meteorites and we have lunar meteorites. And if you look at the transfer probabilities, they're not quite as great coming from Venus outward. It's easier to move things inward in the solar system, and it's easier to launch things off of smaller planets like Mars. Nonetheless, it would be really surprising if there wasn't some rate of transfer. And one thing that I've wondered is if part of the problem is that Venus rocks might look a lot like Earth rocks, and maybe we have some that we haven't recognized. But in my view, it's probably just a matter of time before either in Antarctica or on the moon, or who knows, maybe on Mars. We seem to be finding a lot of meteorites on Mars. Maybe we'll find a Venus rock on Mars.
Yeah, and then good luck with the triple oxygen isotope analysis required to confirm it's from Venus, which, by the way, we don't have a great...
That would really mess us up. That would really mess us up if one of our Mars rocks actually came from Venus. That would like set us back.
Well, here's the thing, right? We know so little about Venus. We actually don't necessarily know what a Venusian meteorite would look like. So, thinking ahead to exploration, Sarah mentioned and Yanish mentioned the different mission classes that people are thinking about for Venus. There's definitely an argument eventually for a Venus sample return, right? Especially because the conditions are so harsh on the surface. Why would you want to try to stick around there and try to do your analyses where you could either land and float back up to the relatively clement upper middle atmosphere, maybe hang out on a balloon or something, or maybe you just bring it back. I like to think audaciously about this, but we would learn so much from Venus meteorite if one exists, but we can bring our own sample too.
Right.
We've already got Mars rocks. What are we doing bringing back more of those? We need a Venus rock.
So David, you were saying how it's more likely to transfer a part of a planet from outer to inner. So what about this idea of perhaps Earth has seeded Venus with life?
Well, almost surely there's been some transfer. It's hard to imagine there hasn't been transfer of Earth material to Venus. There's some ongoing rate because the planets are still being bombarded, and there's a time in transfer where things end up in sort of weird orbits and eventually make their way in. But certainly, if you go to earlier on in the solar system, I mean, just take for instance the KT impactor 65 million years ago. That threw a lot of stuff off of Earth. Surely some rocks from that impactor made it to Venus, and so there's been a rate of transfer. And if you believe that there's no reason to think that microbes would not survive that journey. Microbes are tough. and people have looked at this a lot, all the different things that happen to meteorites in terms of the radiation in space and the shock of launching. There would be survival. And so especially this picture that Bethany was drawing of Venus maybe having been an oceanic planet for much of its history, it seems quite, I would say, not just possible, but likely that some microbes from Earth over time landed in oceans on Venus.
Well, so there is a question here about what planets or bodies or moons would be most likely for abiogenesis, given that they're, as you're describing, could well have been interplanetary transfer, at least in our inner planets. Maybe David or John wants to take a stab at that.
I'm sorry, so what was the question? The relative probability of abiogenesis?
Not the relative probability. It's not a very quantitative question. It's qualitative. Like, if we think Earth, Mars, Venus could have somehow seeded each other, are there other planets, maybe the outer moons, that are more likely to have had abiogenesis? Like, could you be fairly sure there's an abiogenesis somewhere if we find life elsewhere?
Yeah, I mean, especially given this picture that Earth, Venus, and Mars early on quite possibly all had habitable oceans at the same time. The idea that if one of them started, that began the process of life, that it could have spread to the others is not at all outlandish. And so we may or may not be looking for an independent origin. It's much easier to imagine that the interior oceans of the outer solar system, inside of places like Europa and Enceladus, and now there's even talk of maybe Pluto has a habitable ocean in the inside. So it's much more. Seems much more likely that those places would have been sort of permanently quarantined, if you will, from Earth life. And if we found anything on those worlds, it's much more likely to be a second Genesis.
Although, there have been folks who've done those calculations, and while it's it's probabilistically much less likely that Earth transferred something to, say, Europa, it's not vanishingly small. It's sort of in the age of the solar system, it was sort of a few times in a million that arrived.
But if it lands on the surface of Europa, then it's sitting there getting irradiated by Jupiter's harsh radiation field, and it has to eventually end up in the ocean. I mean, I guess it's possible, but I wouldn't, if I was a betting man, I wouldn't put much money on that.
That's my feeling too. And then you go out to Enceladus, and it's about 1,000 times less likely than Europa. You have to construct, a rather circuitous path where the object hits the surface and is warmed enough that it gets, melted into the ice quick enough that the radiation from Jupiter doesn't kill it. And then it has to survive, the millions of years to make it down to the ocean.
Sounds rough.
But I think that opens up a really good question, which applies to Venus, Mars, Europa, and Enceladus, which is one of the reasons why this search for life in the solar system, because it's accessible to us, as Bethany says, we stand on the precipice where we can go to Venus and investigate. We can go to Europa and investigate. We are on Mars investigating with an astrobiology rover. And so these places and the technology we have is accessible. And if we find another biological system, for the first time, we'll be able to ask the question is it like life on Earth? Are there other, laws of biology that are like laws of physics that help guide our thinking that could then be applied to exoplanets, more broadly, and life in the universe? We have no idea whether there are fundamental laws of biology or whether we're just an accident. So this is what excites me.
All right, great. We still have time for some questions. So for our attendees on Zoom, please keep the questions coming. In the meantime, I think we're ready to see our poll results. So IT folks, we're ready for you to share those results. Wow. Out of all the polls today, this one is definitely, it looks like some of the questions here are most skewed. So everyone can see this, hopefully. Do you think Venus was habitable early on? Or when do you think Venus was habitable? It looks like 65% of respondents said early on. Only 10% said today. And I bet a lot of those 10% are people on this panel right here. Do you think Proxima Centauri b is more like Venus, Earth, or neither? And wow, 75% of respondents said neither.
There's a clear winner here. But the question is then what do we, I mean, maybe we should pull the panel. What do we envision that it's like if it's not like Venus or Earth? I kind of poll the audience.
Well, while everyone's thinking about the answer to that, I'll just say I love that. It's in the spirit of that in exoplanets, we've been surprised over and over again. And so maybe surprise is just the norm here. Anyone on the panel want to take a guess as to what it might be like if it's neither like Venus nor Earth?
Well, I mean, you know, the type of planet that we don't have in our solar system, and it's a bit of a question as to whether we ever once had one, was a true kind of water world where, you know, the surface is completely, you know, some sort of liquid medium in contact with an atmosphere rather than an icy shell. We don't have one of those. That'd be pretty cool if one were nearby. So that's maybe one possibility. There are all kinds of bizarre atmospheric compositions, but I won't speculate in that regard. I don't know. What do other folks think?
This isn't very useful, but I keep this line from an Isaac Asimov story keeps popping into my head, which is insufficient data for meaningful response.
John, you're muted if you're talking.
There is a comment in the chat that people suggest that Proxima's NB could be tidally locked, and that makes it really distinct.
My point was, as Bethany said, we don't have super Earths in our solar system, and you know there could be whole different types of environments that could create different types of life.
All right, here's one. Will a snapshot of the Alpha Centauri system yield multiple habitable worlds like our solar system, one habitable world, or no habitable worlds? And here there's a slight edge to the multiple habitable worlds. But I think it may be, we think that all stars have planetary systems, more than one planet. Although we're not super sure about binary stars and how much space there is for multiple planets. But that one might be just more like wishful thinking.
I like the optimism of this audience, right? And it says we have to go test that.
Well, if we visited our solar system to like 3 billion years ago, we would have multiple habitable worlds. So,
and not ones at the edge where we sit around on a panel and debate about it, like ones that are, we'd all be like nodding our heads.
Well, in our last 5 minutes or so panel here, we're going to really have to ramp up our efforts, because on the last question, where should we prioritize the search for life? Venus was a close tie for last. And the question—
for life as we know it.
Well, the question was for life, period. And here the choices were Mars, Europa, Venus, Enceladus, or Titan. Europa is the clear winner at 39%. Mars not too far behind at 31%. Enceladus comes next. And then Venus is at 8% and Titan's at 7%. Okay, I think we can stop sharing that poll. Thank you, everyone. It was great to see some consensus there. So I guess in the last few minutes that we have, I think I'd like to hear more about I think we need now, unfortunately, to hear more about the case for Venus as an astrobiological target. Maybe, Yanish, if you could summarize something super complicated very briefly about the new results, which may indicate that the clouds are not as acidic as we know, and they actually might be just only, it's kind of strange to say this, but only as acidic as the most acidic place on Earth, which is still tolerable.
Yes, on one of my slides, I had this nice picture of Venus with various models of molecules, and there were a couple of molecules there that actually looked pretty normal, like sulfur dioxide and water. Those are not necessarily signs of life. But what is quite interesting is that how their profiles, how their abundance looks on Venus in the Venusian clouds, and how does it compare to the modeling? And we really cannot the observations that we have for those two gases and the modeling doesn't really match. And a very recent paper by Paul Rimmer actually tried to find a solution for this apparent discrepancy between the observed abundances of those gases in the clouds and the models. And what is the interesting, one of the possibilities from that model, from that calculations that he did, is that the profiles of these two gases can be actually reconciled with the modeling if the pH of the cloud droplets is actually as high as 1. So we can imagine that if we had just the droplets of sulfuric acid, we would actually, the acidity would be so low that we wouldn't be even using a pH scale to measure it. We would, for example, employ a Hammett acidity pH, Hammett acidity acidity scale, which is like minus 11.5 in if we are applying it to concentrated sulfuric acid. So pH 1, if this is indeed the case, if indeed some, at least a fraction of droplets or aerosols in the clouds of Venus is actually at pH 1, then it's actually within the habitable levels of pH for life as we know here on Earth, because some of the extremophiles here on Earth actually can survive in that pH. So I often joke that if indeed Paul Rimmer's paper is correct, then clouds of Venus might be more like Atacama Desert than a test tube of sulfuric acid. And that might actually change a lot in our perception of the planet and its habitability and its current habitability.
All right. Well,
I would say that the real aspect of this is that the question is so important. Yes. We just have to look, right?
We just have to look. Yes. There are only a few things. Yeah.
I've got another point I'd like to make about Venus, though, as a place to look for life. You know, we tend to often think of the search for life in terms of finding just a specific environment that has the right conditions. Does it have the right temperature, pressure? Is there water? Are there organics? Is there an energy source? That's one way to think of life. But if you can also think of planetary qualities. And on Earth, the one planet we know of with life, we inhabit this interface between these two great active heat engines. There's the interior engine of plate tectonics, which renews the surface and resupplies nutrients and gases. And there's the exterior heat engine of the atmosphere. And both, which, you know, drives the water cycle and so forth. And it's the combination of that interior and exterior heat engine and the fact that we live on the interface that makes Earth such a great place for life. We don't know very many other planets, certainly in our solar system, that have that combination of qualities. But post-Magellan, we know that Venus does. Venus has been an active planet and has that renewable quality in its surface and in its atmosphere, has geochemical cycles, which could drive biogeochemical cycles. So personally, once I learned about the Magellan results and saw how active Venus was, I thought, well, it has the qualities of an active planet that could drive an active biosphere if we relax this assumption that life has to be exactly like Earth life. It has those planetary qualities. And that was before I learned these recent modeling results suggesting that Venus may have had surface oceans through most of its history. It could have been the planet next door with an ocean while Earth was evolving life and evolving complex life and going through all these transformations of photosynthetic life and so forth for billions of years. Venus was right there all the time, apparently, quite possibly with surface oceans. And to me, that automatically makes it really intriguing for astrobiology. And then the question is, what happened when those oceans went away? Did life just die out, or did life do what life does and find an available niche? So that history combined with that active planetary quality, to me, makes Venus a more promising place, even in my view, and you may think I'm crazy, than Mars. I'm supportive of Mars exploration. I want to know if Mars should have had an origin of life. Today, Mars seems like a dead planet to me in terms of interior geology, which is driven by an active interior. There may be little hot springs underneath somewhere, and maybe life can hang on in an environment like that in a planet which is otherwise dead. I don't know. I'm in favor of looking to find out on Mars. But in terms of that robust, active cycling quality of a planet, which is so important to a biosphere here on Earth, Venus is really the other planet in our solar system that has that. So I totally think it's worth a look.
All right, thanks, David. And what a great, strong way to end our panel. I'd like to thank all of the panelists and the people who've asked us questions today. And I'm going to turn it over to Pete Worden for some closing remarks.
Well, thank you to everybody. This was really a great day and a great discussion here, where to go in the solar system. I have to say my choice is Venus, but that's my personal preference. But it's been a fabulous 60 years since Yuri Gagarin first went to space. Our future is unlimited. Tomorrow we're going to be talking about actually going to Alpha Centauri and how to do that. In the meantime, I fixed myself a Manhattan. So I'd like to propose a toast. If you don't have drinks, you do it mentally to Yuri Gagarin and all of the space explorers and scientists and all over the future that are going to make these wonderful futures a reality. So here.
Cheers.
Cheers. And we'll see everybody tomorrow.
And thank you, Sarah.
Thanks, folks. Great panel.